Hi everyone. First, introduce myself. My name is Santosh BJ, Department of Computer Science and Engineering, working as an assistant professor, BGSIT, Aditya Engineering University. Today, I will present on one topic and sequential multiplication in computer organization. So, how we will solve the problem using sequential multiplication? All of you know about the normal multiplication, how we can solve. Same way, in the what are the concepts, how we are solved using the sequential multiplication, and we explain how its sequential circuit works. So let's see first. So sequential multiplication. So let's understand some concepts or some rules of sequential multiplication. So what is the rules first? Or what is the concepts we are using sequential multiplication? So normally we are using array multiplier or array multiplication. So here it requires some large number of gates and large number of adders for multiplication process. So in sequential multiplication, overcome that problem instead of using that all those things. In the arithmetical logical unit only, we are some circuits are available for sequential circuit. Like what is that? That is a shift registers. That is for multiplication process or multiplication operation. So that is a rule. Next, multiplication performed by single n-bit adder. So here in the sequential multiplication, we are using n-bit adder. So why we are using n-bit adder is nothing but addition process. So each and every time we can add. I will explain in the diagram. You can add. I will explain the diagram. See, this is an n-bit adder. So n-bit adder is used for only addition process. Next, we will further we will explain in the diagram only. So now you understood only the single bit n-bit adder for use for the addition purpose with n number of times you can add. That is a one. Next, in register A and multiplier Q. So here we called as A naught, A n in the diagram only. Once again, I will show that in the diagram. See, that is A naught, A2, A1, A2 up to A n number, A n minus 1. Q naught, Q1, Q2 up to Qn minus 1. And C. C is nothing but what? Carry. So here the register A and multiplier Q together holds the partial product. So once if registers and multiplier, it holds the partial product. Before multiplicand and multiplier, before multiplication, initially the register is 0000. That generate the signal. Add or no add signal is generated from control sequencer. If it is add and if it is not. So when you add and when you know add process, I will explain the diagram. Next, after the partial product, that is the m number of bits or m number of bits to partial product, you get the partial products in the number of steps. Then it will generate each and every step partial product a plus one step. So when control signal is sent to the addition, if you send the add signal, then control sequencer generate with add for multiplicand and registers. So then automatically it contains the cycle, once first cycle, second, and so on. Each and n number of cycles. That is nothing but partial product I plus 1, next partial product I plus 2, and so on. So another basic thing is, on all other sides, we are shifting left in the normal. But instead of shifting left, we are here in the sequential multiplication. So partial product is shifted one bit right position, not left position. This is some basic rules. So now we more understand when we analyze with the diagram. I will explain now. We move on to this diagram. Circuit, sequential circuit multiplier. See, already I told that in the first n-bit adder. See, this is n-bit adder. Initially, it is also 0. When control sequencer for sending adder no add control for using this control signal, understood? And carry and A naught or A1, A2, AN, that is called as register A, we called as. So before starting the process, either multiplier and with multiplier. So it is initially it is 00. It is more understood when you solve the examples. So just in the diagram, how it works. So if it is in the initial position, it is A naught. These are all anything. This is number registers. So initially we store the values as 0. If you are okay. Next, multiplier. We can take any multiplier as a 1 binary numbers. 8, 13, or we can write it in binary values. Same multiplicand. We can take 11, 12, and so on. So that is multiplicand. So here, first, that is a, I already told that instead of you shift left, you can shift right position. That's why it is stored in line. This works on shift right position. Then already I told that add and no add control signal. So when you add and when you no add, already I told that we will explain the diagram. So in the diagram, the least significant of multiplier Q. Q we understood first. Q is nothing but multiplier. M is nothing but multiplier. So instead, here check least significant in multiplier, not multiplicand. All of you understood? Least significant bit is 0. So obviously there is no add control. The control sequencer send no add signal. So control sequencer send no add signal. So as it is, what is there in the register, you directly write it, and what is there in you can in the shift no, sorry multiplier, you can write it as it is. Same thing when the least significant bit is 1, so automatically send add controls to the control sequencer. So control sequence, when you send the add signal to the control sequencer send to the multiplicand. So add this multiplicand. Initially it is also 0. So when you send the add signal, the multiplicand add with the registers. This is another important step. When you send the add signal, so this multiplicand, what is the value? You will take any 8, 9, 10, 11, and so on in the binary numbers, zeros and ones. So that multiplicand will store with add with these registers. So that is nothing but when you add, if you add registers and multiplicand, if any carry comes in the most significant bit, after most significant bit, that will be stored in C. There is no carry when you complete this position, so obviously it will be 0. Okay, I think you understood. After that, shift right one bit position. Shift first C will copy it into here, and this value is copied into another right position. This will copy into another right position, and so on. So when you after completion of shifted, obviously after shifting anything 0 or 1, so automatically here reset the value. So that is nothing but how we will work the sequential multiplier. So now we'll done. I'm more confident about in the sequential circuit multiplier. So we solve one example or we solve one problem. Then we'll more understand about this concept, how it works. One diagram and some basic rules and one example. So this is an example. See it. This M is nothing but this is a first step, that is initial configuration. What is the initial configuration in the diagram? See, carry, write it carry here, and write A0, A1, A2, An minus 1 we called as registers, and Q0, Q1, Q2, Qn minus 1 we called as multiplier, and this M multiplicand. M is nothing but multiplicand. So when you send the add position, we can add with multiplicand. So that's why in the problem you write it as a multiplicand in above the registers. That is the initial count. And as it is, all other are same carry right here. In the right side, we can write registers, and the right side multiplier you can. But in multiplicand, we can write it upper side of the registers. A. So let's move. So I will write M, we will take, then the other example will take 8 plus 4 plus 1, 13. We'll take multiplicand, the value is 13. See here, see how we'll write in the binary. All of you know about how you write in the binary form. No need to explain in this session. 8, the 8, 4, 2 is 0, and 1, 1. So total 8 plus 4 plus 1. So 8 plus 4 plus 1 is 30. So now we'll take multiplicand value is 30. And C is initial, it is 0, already told. Even registers also already told that when you start with multiplicand multiplier, or you can send this control sequence to add n adder bit. So you can use 1-bit adder also. Before you can start any process, so initially it will be 0. So that's why we'll write it as how many number of bits you will take. That will be 0, 0, 0, 0. Will take 4 bits. You can put it 4 bits. 0. So another one Q, we can take it as multiplier. So multiplier will take it as 8 plus 2 plus 1 means 11. So 13 into 11. So what is the product of 13 into 11? So 143. Totally 143 is the answer. The normal multiple 13 into 11 is 143. You take it like that. So how we will add in the sequential circuit? How will works in the sequential circuit? So let's try. That is the initial configuration. All of you know how to write the initial configuration. So carry, that is register, that is Q. Q is nothing but multiplier. Once again, you understood Q is nothing but multiplier and M is nothing but multiplier. There is what? There is no confusion at all for writing multiplication and multiplier. So first we take it as multiplier is where you will write in the right side of the registers. You can any exchange the M and Q, the answer will be. So that's why always I write it that the multiplier is nothing but Q. You can write always in the right of the A, means registers. In upper side of the A, you can write it as M, that is nothing but multiplicand. So if you write like that, next, then if you understood this much, then you will solve easily. So that is nothing but initial configuration. So first we'll write it as initial configuration. After that, then already in the diagram we show that we explain that. 1 minute, sorry. In this example, I already told that in this diagram. So carry what I told. So that is initial configuration. After initial configuration, the cycle first. So what is the cycle first? See, if Q naught here, the least significant bit of Q naught. Let's check the least significant of Q naught here. Understood, guys? The least significant of Q naught is 1. Okay. If least significant bit of Q naught 1, then you can the control sequencer send the add. There is an add signal. So add what what are the contents? What are the data you can add? One is registers, what the data will store in the registers, and what you will take as multiplicand data. So add both multiplicand and registers. So check once. Now we can move on to the add. So that is multiplicand, and that is registers. 1 plus 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1. There is no carry, can obviously. So we will consider as 0 is the carry. Next, shift as it is right, Q. Q is nothing but what? Multiplier. So multiplier, we can store 1, 0, 1, 1, same as it is. So next, 0, you can shift after addition process, you can shift right position. So what is shift right? Now, that most significant bit is 0. It is the carry. What will the data will be stored in 0? That will be stored here. Shift right. Next, the 1, next process 1. The 1 will be stored here. Next right position. Next, this 1 will shift right another position. Next, this 0 will shift right here, means here. Next, this 1 will shift right. Next, this 1 will be come to here. Next, this 1 is come to here. This 0 is come to here. This 1 is come to here. So that is nothing but the first cycle is completed. So next process, once again, add or no add. So let's see. So now what is there in the registers? This is after this step. First step end with 0, 0, 1, 1, 0, 1, 1, 0. That is called as partial product. PP1. Now we are on PP1. That is the first cycle. That is or we call as PPI, I position. So that is a partial product of I. So now let's check what is the least significant bit of Q? So here least significant bit of Q is 1. 1 is nothing but you can add. If it 1 comes, directly you can add. So what are the contents? So what are the data we can add? Which one we can select it? So what is there in the registers and what you will take it as multiplicand. So in the first cycle, after first cycle, you can add with this data, add with this data. So add with the multiplicand. See, this is a multiplicand. So in the first cycle, 1, 0, 1, next 0, 1, this one with the multiplicand, that is 1. Next, 1, 1, here multiplicand also 1, register also 1. 1, 1, 0, carry 1. So 1, 1, 0, here 0. So 1, 1 is 0, carry 1. So carry 1, write it in the C. Okay, you can take 1, you will get the carry, and also as it is 1 will come, the 1 will be stored. If it 0 comes, 0 will be stored. No, don't worry. So that is the process add. In the second cycle, add is complete. In the same process, next process is very easy. So obviously this one, what is there in the carry, that will shift 1 bit right position. Where you will shift? So this 1 will come to the right side, 1. So in the register, in the most significant bit of register. So see here, this 1 will shift it to 1 here. This register will shift it to here. Next, this 0 will be shifted to here. Next, this one minute. Yes, this one will be stored to here. And another one, same as it is, this one is shifted to here, this one is shifted here, this one is shifted here. Finally, this 0 is shifted. So that is complete your second cycle. That is complete your second cycle. So next, so after that, that is a second cycle is completed, is nothing but we can get another partial product or PP2, partial product of second cycle. So then there is a final partial product. Next, move on to the third cycle. So you can check whether what is there in the result. Just 1 minute. I'm sorry. It is 1110. Yes. Here, what is there in the result? 1 minute, you will check that is whether it is 0. That will be 0. Yes. You can add or no add. That is control with add or no add signal. That will vary. Yes, here some mistakes. 1110, 0 will be here. So here, that is good. Sorry, here some little bit mistakes. So when the least significant bit is 0 in this diagram, means here, and the least significant bit is 0 in the third cycle, that we compare with this 0. Least significant bit is 0. Nothing but no add. I mean, some mistakes add only, right? That is nothing but no add, guys. Okay, no add, you write as it is. What is there in the register and what is there in the multiplier as it is copy. So this is the carry and this is the what is there in the register 1001 as it is we copy and 1110 as it is we copy here. Okay. After that, shift right, correct? After that, shift right. The third cycle, see, 0 copied to here, 1 will be shifted to here, and 0 is shifted here. This 0 will be shifted here. This one is shifted, and so on. Finally, third cycle is over with the answer is another partial product 0, 0, 1, 0, 0, 1, 1, 1, 1. That is third cycle will complete. So next we compare with another least significant bit that is 1. So if you send 1, obviously it is add. Pass the control step to the sequencer, you can add. Then control sequencer will add with them with what? With the multiplicand. This answer, that is nothing but register. What the data, or what the content will be stored, what the data will be stored in the register 0100. That data will be added with multiplicand, means 1101. So now you can add with this m to this 0100. See here 101. There is no carry. 0 and this 0 is 0. Next this one and this one 0, carry 1, carry 1. That is 110 with this 00, carry 1. Let's say we can get the answers. So obviously you can, after the add is over, you can shift right. This one is copied here, and 0 is copied here, 0 is copied here, and 0, and so on. So final answer is this. After 4 cycle, you get the fourth product. That means totally, finally you can number of PPI, and can get the final answer with the partial product, number of partial product in n number of times using adder circuit, n bit adder. So we can get, so whether the result is right or wrong, already I told that here what is the multiplicand value, 8 plus 4 plus 1 means 13. Here what is the multiplier value, 8 plus 4 plus 1, sorry, 8 plus 2 plus 1 means 11. 13 into 11, 143, 143. So 8, 4, 2, 1, that is 15. Here totally sum is 8, 4, 2, and 15. Total value is 15. Here 16 bit is 0, no, 32 bit is 0, and 64th bit is 0, and 128 is 1. So 128 plus 50. So 128 plus 10, 138 plus 4, 15. Correct. 128 plus, first you can consider as 8, 136, sorry, 64, 64, 128. 128 plus 128, 136, plus 4, 140, plus 2, 142, plus 1, 143. So we get the final answer. So let's try another example with simple example where no add circuit, any under with more understanding or more with the no add and add combine with the add and no add. So in the last example I did missed it. Here we can, if it is 0, you can no add, guys. So same way here no add, I will write correctly. So here 8 plus 4 plus 1, 13, and multiplier is 8 plus 1 is 9. 13 into 9. What is 13 into 9? That is 117. I think 117 is the answer. Yes, 13 into 9, that is the 117. So let's, all of you understood the initial configuration. No need to explain more here. Write the initial configuration first. So what is the least significant bit? 1. If it is 1, you can add with the multiplicand. So see here multiplicand and register. Initial register is 000. So check here 101, 0, 1 plus 0, 1, and 1 plus 0, 1, 101. And carry is 0. And write Q is as it is. The add and the addition is over. Next condition is shift right 1 bit. Okay. So okay, the shift this carry 0 is there, no? You can shift to the most significant bit of register. So this 0 is shifted to here. This one is shifted next 1 bit right. This one is shifted to next 1 bit right. Next this 0 is shifted to next 1 bit right, and so on. So finally we get the first partial product, that is 0, 0, 110, and 1100. So here the least significant bit is 0, nothing but no add signal. So no add signal is nothing but as it is what is there in the register, you can write it, and what is there in carry, write it. Same copy into the what is there in the queue, write it. Nothing but same in the previous cycle after shift, that is 0, 0, 110, and 1100. As it is, you write it. Check here. Same thing will be, not this step, same thing will be copy paste here. There is no changes. Okay. Okay, after that you can shift once again. This 0, this 0, this 1, and this 0 come here. Finally, another also is significant bit is 0. Once again, we no need to add. So same as it is, see 0, write it. 0011, same 0011, write it. 0110, same as it is, write it. Okay. Next, add once again. If you add this 0 here, this 0 here, this 0 and 1 bit right position, I can add. So finally, you can after add it comes 1. So 1 is nothing but you can add. Add is nothing but what? This 0001 is nothing but what the currently registered data, the currently register holds the values. Currently 0001 is stored in the register. So we can add with the multiplicand 1101. Okay, not add with 0011. You can add with the multiplicand. Here, some all of you then did the mistake. You can add with this one. No, that is wrong. If you add with this register, finally, what the values are stored in the register, that will be called add with their addition with the multiplicand m. So that is number multiplicand m is 1101 and current value stored in the register is 0001. So add here 110 carry 1. So here 0 is there and here also 0 is there, but carry 1, you can write the carry 1. Next, here 0 is there and here 1 is there, write 1. Next, here 0 is there, here 1 is there, write 1 and carry 0. There is no carry in the final. So 1110 and 101 write it as it is and shift right 1 bit in the air. So if we shift right, so final answer is 0, 0, 111 and 0101. So let's write it, check whether the value is correct or not in this. See here, what is the answer? Final answer 00311. Not see here 00311 and 0101. 00311, 0101 is the final answer in the fourth cycle. So I will write here and we can not confuse about the previous one. So here I can shift how we'll store the binary values like this. First 1 bit 1, 2, 2 plus 2 4, 4 plus 4 8, 8 plus 8 16, 16 plus 6 16 32, 32 plus 32 64, 64 plus 64 128, 128 plus 128 256. Like this manner you can store 256 plus 256 white file. Like this you can store the values. See here I will take now I get the answer in 5, 2 plus 3, 5 plus 4, 9 digits. So that's why I'll write it here. There is no confusion in this. So here 0, 0 is no calculation. 256 also 0, 128 also 0. The 64 bit 1 is there. So data will be present. So 64 write it here. 32 also 1. Yes, write it here 32. And 16 also 1 write it here. 8 once again 0. Neglect it. 4 only 1 is there. So we can copy 1. Sorry, copy 4. And even 2 also 0. No need to take. 1. Yes, that bit is present. So 1 will take. So add 64 plus 32 plus 16 plus 4 plus 1. So answer is 117. So what we will take as a multiplicand and multiplier in a normal. If your same answer will becomes in the sequential. How it will be circuit works. So this is the way our circuit works, sequential circuit multiplier. So I think all of you understood this concept about the sequential circuit multiplication. Next, we move on to the Booth algorithm. And next, let's see in the next class. Thank you. Thank you, one and all.